Ultimately, Heisenberg groups will simultaneously be manifolds, sub-Riemannian manifolds, and also Lie groups. But to keep things simple, we want to go one step at a time. In this lecture, I want to mention and describe the sub-Riemannian structure of Heisenberg groups without actually talking about any sort of Lie group or group structure. And to keep things even simpler, I'm only going to work with H1. Let's recall some basic language from differential geometry. We have a smooth manifold. In particular, at every point P, there is a tangent space TPM, as you see here in red color. And all of these TPMs are isomorphic to R to the dimension of the manifold, but not in a canonical way. That's important. To be able to do geometry and measure length and angles, we need also to have what is called a Riemannian metric on this manifold. G here denotes an association of an inner product to each and every one of these tangent spaces. If you take two vectors from two tangent spaces, they are never equal, and they are not even identifiable in a canonical way. Therefore, you can dot product two vectors if and only if they come from the same tangent space. This is not a problem for measuring length of speeds or speeds of curves, length of the velocities of the curves. If we have a smooth curve, which is definable because we are in a smooth manifold, gamma prime is a vector in the tangent space at that point gamma t. Therefore, in particular, we can dot product gamma prime with itself. This G in reality means G, the inner product at the point gamma t. So technically we should be writing get G at gamma t, but that just takes the notation out of control. So it's understood that this dot product is happening at this particular tangent space, and when you dot product a vector with itself and take a root, that defines a norm on that vector. It's a non-negative number, so we can integrate this function over the interval of parameterization of the curve to define the length of the curve. Sub-Riemannian manifolds are constructed out of smooth manifolds. But Heisenberg groups are especially simple because the underlying manifold is just a Euclidean space. Hn for natural number n will be constructed using R2n plus 1. In particular, H1 will be R3, which we will focus on for this lecture for simplicity. Now, something about Euclidean spaces makes them even more special among manifolds, and that is there is a canonical way to identify vectors from different tangent spaces. Given a point P, we can, and a vector V in TPM, we can canonically translate that around the space. So there is another vector in TQM which in a canonical way corresponds to the chosen vector from TPM. And in so doing, we can even suppress the notation and call the vector field just by V. So V can also be seen as a vector field rather than one vector in one tangent space. Therefore, we don't even have to specify the base point. The reason this exists is indeed because our case with the addition are vector spaces, and in particular they are Lie groups, so the operation of addition of a vector is a smooth map, therefore its derivative takes one tangent space to another tangent space. So this will be the derivative function of f, where f is translation by, say, P minus Q. So that P maps to Q. I incidentally happen to be teaching multivariable calculus this summer, and I kind of wanted to tell my students that the reason or the way we identify vectors from different base points is actually independent of a choice of coordinate system. And in this point of view, it's clear why everything is quite intrinsic and independent of a choice of coordinate system. But of course, in an undergrad course, you just don't mention things like that. So as a vector space, also Rn has a special point denoted 0. From the manifold point of view, 0 is no more special than any other P or Q. But what this point enables us is we can make a choice of coordinate system, which is basically a choice of basis for the vector space Rn or Rk, and then use it to describe every given point as an n-tuple of values. So unfortunately okay, so you can say P is X, Y, and T once you fix your coordinates. And also when you fix your coordinates, let me actually stick to the color red. So once we fix a coordinate system, again, that means just making a choice of basis. There arises these vector fields, global vector fields, partial x, partial y, and partial t. This is choosing this v to be one of your coordinate axes. This looks like partial y, and then translating it in that canonical way all around the space. Therefore, we don't need to really say this is the vector field at the point P, because again, it's canonically identified to the one happening at 0. That is why we suppress the notation, the dependence on the base point in Euclidean spaces. So we started with a manifold, which happens to be a vector space. Therefore, we can identify vector fields all around the space. I'm mentioning this, of course, we're looking at just R3, and there was no need for this much rant. The reason I'm doing this is because we will actually soon forget about the addition structure on R3 and instead talk about a different group structure. And this is kind of a preparing for that in future lectures. Anyway, now that we have these vector fields, we can describe any other vector field in terms of linear spans of the 3 here, because at every tangent space they form a basis, right? Partial x, partial t. This new group structure that we will see will dictate us to consider a different triple of vector fields. Those will be the natural vector fields from the viewpoint of that group multiplication. But we can still use this coordinate map, this coordinate chart on our manifold to describe them. So if we are given a point x, y, and t in our manifold, we define three vector fields as follows. So the vector field x at P is given by partial x plus 2 times y partial t. We see here that the vector field definitely depends on the point P because we need to get this y from that coordinate. And therefore we cannot really drop the notation xp in this coordinate system, of course. From the viewpoint of the group structure that we will have, x actually will be well defined without even putting this p down here. But here we're using two structures. We're cheating. We're using the familiar coordinate system that we have, where we start with, where we look at R3 with the plus as a vector field, vector space. But we only use it to be able to describe the more intrinsic objects of the other group multiplication. So again, this lecture we won't get into the details of the group structure, but we use it as a motivation to explain that these vector fields that I'm writing now come from a reasonable place and there is good motivation behind them. So we haven't defined the group structure that I mentioned, but there is no harm, there is nothing stopping me from considering these three vector fields. These are smooth vector fields because all these coefficients are smooth in this particular coordinate chart that we have for the manifold. And so let's see what we can say about these vector fields. So at every p, these are linearly independent. Which is a simple exercise. Just write axp plus byp plus ctp equals 0 and prove that abc must be all zeros. The reason is that partial x only appears here, so a has to be 0 if we're not going to end up with partial x. Then b has to be 0 for analogous reason, and then that forces also c to be 0. Another thing we see is that at the point p equal just 0, 0, 0, x, y, and t are just the standard partial y and partial t. So right at the origin they coincide with the other standard vector field, but as soon as you leave the origin they become different. We see that, for instance, as y becomes larger, these vectors become x becomes really large, these vectors become extremely long from the Euclidean point of view because the length becomes 1 plus 4y squared root. So that is this. The other one is that the span of xp and yp never contains the vector tp. And of course this follows from the previous claim that they are linearly independent. But I wanted to mention this. Geometrically, this means that the plane is never vertical. there is a special name we give to this span of the two vectors xp and yp. So xp and yp will be the distinguished vector fields here, and t will be treated often very differently. So the definition is, we call span of xp, yp the horizontal subspace or horizontal subbundle at P, and denoted by, let's say, horizontal at P to H1. Okay, so that's the definition of the horizontal space. Okay. We also now begin to diverge from the Euclidean geometry by playing around with the inner product. In the standard Euclidean space, we declare these vectors, partial x, partial y, and partial t, to be unit vectors and perpendicular at all points P and Q. So independent of the base point, we always declare them to be orthonormal bases. Remember that we could keep the vectors as they are, but still change the inner product. For instance, we can say that the same vector partial x has a larger length at q than it does at 0. So it is technically possible to scale the metric that way as well. But here we change the Riemannian metric totally so that we equip H1 with the unique metric, Riemannian metric, such that xp, yp, and tp are unit length and mutually perpendicular. So let us call this the inner product of vectors G. This is the reason such a Riemannian metric exists is actually right there. We define it by this property. It just remains to show that this property does define a smoothly varying inner product from one point to another point. If you are given a finite dimensional vector space, you can always equip that with an inner product by fixing a coordinate, by fixing any basis, E1, E2, E3, just linearly independent collection of vectors, and then you declare them to be, so you can equip them with the inner product by declaring them to be orthonormal. This is what is happening here. So at every point, from the above observations, at every point, we have these new vectors. So let me also draw these. So what is happening is that under this new geometry, I'm not looking at quote-unquote parallel transportations of x, y, and t directions, but rather I have totally new vectors. So at the point P, it will be partial x, but then there is this additional partial t to it, so it will be something like that. and then y direction, maybe it goes this way, and then t part is always just partial t. So these vector fields change this way, and at every point they span the tangent space at P. So a way to define an inner product on TPM is just declare these vectors to be orthonormal. And because these vectors vary smoothly, the resulting inner product G will vary smoothly. So it's a definition / proof that such a Riemannian metric does exist. So this is a very important departure from Euclidean space. The vectors xp and yp, as we saw above, would be very long if we just worked with the standard inner product. But then we see that, let's say this is my unit 1, right? This is scale 1 from the Euclidean point of view. In the new, the vector xp can be really long. Let me actually make it really long if this thing is going to allow me, which doesn't. So annoying. Okay, so xp may look like really long from the Euclidean point of view, but from the viewpoint of G, this still has length 1. And this necessarily means that partial x length, partial x's length will depend now on a P, on what point you are looking at. So previously all of these partial x's had unit length in R3, but now that length changes from one point to another. They become actually very short because the much longer xp's have length 1. So this will have important consequences, and when we reach there I will mention them. For example, this will have consequence for length of projection of a vector versus the vector, a curve, projection of a curve versus the curve itself. So what do we do with this horizontal subspace and with this new norm on R3? The answer is we are going to construct a new metric on R3. So definition is we call an absolutely continuous curve from a compact interval into R3 horizontal. So we will call such curves horizontal if gamma prime of t, which exists because the curve is absolutely continuous. And here when we say absolutely continuous, we're using the standard metric. So this is where a lot of cheating happens in dealing with Heisenberg group. Intrinsically, we are getting rid of R3 inner product and R3 invariant vector fields and stuff. But we cheat by using it as a coordinate chart to write down explicit formulas for vector fields and other constructions. So here, for instance, we use a priori structure of R3 to talk about absolutely continuous curves, and then because now we know from Rademacher's theorem, for instance, that these have derivatives almost everywhere, this is a vector, so we require that this belong to the horizontal subspace. That is, of course, gamma prime of t is a vector at gamma t, so this will p will be gamma t of h1, which, let's recall, is simply the span of the vector field x at gamma of t and vector field y at gamma of t. So if this is true for almost every t in A, B. This also means that if gamma prime of t is simply parallel to partial t, it won't be horizontal because this does not belong to the horizontal subspace at any p. That immediately tells us that the curve that simply travels this way, the curve that goes in this direction, is not horizontal. Yeah, because the derivative is parallel to partial t, which does not belong to pH1 unless that derivative is 0. So let's recall our basic instructions. We have very special vector fields x, y, and t. We choose x and y, and their span is a plane. We call it the horizontal plane or horizontal subspace. And then we put a metric in which these x and y's are orthonormal. And now we define a curve to be horizontal. Next, we define the length of the horizontal curve. We define the length of gamma to be, well, you integrate just as in abstract Riemannian manifolds. You have gamma prime of t, you multiply it, dot product with itself with respect to this g, you take root and then you integrate. Okay. And final definition, because I promised we will construct a metric on H1, given P and Q in H1 in R3, we define the Carnot-Caratheodory distance of P and Q to be the infimum length of gamma such that gamma is horizontal and joins P to Q. Okay, one thing we see immediately is that this is never 0, and it's quite also easy to see that DCCPQ is symmetric, because if you travel a curve backward, it's still horizontal, but other properties are not immediate, but other properties of being a distance function, so here metric is used in the sense of metric spaces, being a distance function are not immediate. Maybe triangle inequality is what is not immediate. In fact, we don't even know why this should be a finite value. Y is DCC PQ even finite? Because is there even one horizontal curve joining P to Q? In my picture, I just showed you that the obvious path from this point to that point, if they are vertical on top of each other, doesn't work because it's not horizontal. And a horizontal curve, remember, has to, at every point, respect the plane, the horizontal plane at that point, which is two-dimensional, not in a three-dimensional world. So your velocities are always restricted. So is there a way to still connect without violating that, to still connect any given pair of points P to Q? And we will see that there is a positive answer under some assumptions in a much more general setting, and let's not dive into that at this point. But the theorem, the consequence of the theorem that I mentioned will be that H1 with this CC is indeed a metric space. So we have succeeded in avoiding, quote unquote, avoiding any group structure on H1. We haven't defined any group multiplication, but cheated somehow to borrow the vector fields x, y, and t, and from there construct what is called the Carnot-Caratheodory or the sub-Riemannian metric on H1. So this DCC is also called a sub-Riemannian metric. And now we have an interesting example of a metric space. Interesting because, for instance, the Hausdorff dimension of H1 with this metric is 4, although it's R3 as a topological space, which means its topological dimension is 3. And of course, there are many more surprising facts about Heisenberg groups, even just H1. And that's why this metric is quite interesting. We will get into details later on. So far, again, we just looked at H1 as a manifold. We looked at special vector fields, and from that constructed a metric. In future lectures, we will talk about the group structure and how that group structure goes hand in hand with this metric. Until then, have a good one, and please feel free to put your questions in the comments. Thank you a lot.